When we talk about the old claim that drinking alcohol destroys brain cells, it's important to set the record straight. Pure ethanol poured directly on living tissue will absolutely kill cells, and that's why it works as a disinfectant. But the reality of human drinking is far different. No matter how much a person consumes before reaching the point of lethal poisoning, the concentration circulating through the bloodstream isn't high enough to annihilate neurons outright. The long-standing slogan that every sip of alcohol kills thousands of brain cells simply doesn't hold up under scientific inspection. Evidence for this surfaced decades ago. In 1993, researcher Greta Jensen and colleagues undertook a careful study, counting nerve cells in post-mortem samples from both long-term drinkers and people who had not abused alcohol. They compared brains cell by cell, neuron by neuron, to see if there was any measurable difference. Their conclusion was striking. The density of neurons, as well as the total number of nerve cells, was not significantly different between the two groups. That discovery debunked the notion that alcohol shrinks the brain by direct destruction of neurons. Later studies revisited the same question with newer tools, and the results confirmed Jensen's original findings. This means that even individuals with years of heavy consumption, people who might drink far beyond healthy limits, are not actually losing brain cells from the alcohol itself. However, this doesn't mean alcohol leaves the brain untouched. The chemical exerts a wide range of effects, many negative, some surprisingly beneficial, but none tied to wholesale killing of neurons. On the positive side, moderate drinking, meaning consistent but not excessive use, has been linked to protective effects as we grow older. Scientists in Italy, at the Catholic University of the Sacred Heart, tracked mental decline in older adults. They found that nearly 30% of people aged 65 and above who rarely touched alcohol struggled with cognitive decline. By contrast, only about 19% of those who regularly consumed modest amounts experienced such impairment. This pattern held true across groups with other health conditions as well, pointing to a consistent link between moderate alcohol use and reduced risk of dementia-like problems. It doesn't mean alcohol is a cure-all, but it does suggest small amounts may stimulate protective pathways in the brain. Now, turning to the darker aspects, the picture becomes more complicated. While neurons themselves don't die directly from alcohol, their ability to communicate can be seriously disrupted. Messages in the brain travel through intricate branches called dendrites. These extensions receive signals from neighboring neurons and pass them to the cell body. Alcohol, particularly in large and frequent doses, can damage those delicate dendritic structures. Once compromised, the efficiency of electrical and chemical signaling between brain cells declines, leading to sluggish communication networks. The good news is that the human brain is incredibly dense with connections. Roughly 100 billion neurons supported by tens of billions of glial cells, all woven into a vast signaling web. Because of this redundancy, the damage caused by alcohol doesn't immediately cripple the system. Even in long-term drinkers, if alcohol is reduced or cut out altogether, dendrites can repair themselves, and much of the lost communication is restored. That resilience allows many people to recover functioning after quitting heavy use. Yet not every consequence is so easily reversible. Extreme, persistent drinking can set the stage for serious neurological disorders such as Wernicke-Korsakoff syndrome. This condition manifests with confusion, problems with coordination, vivid hallucinations, memory gaps, eye movement issues, and in severe cases can end in coma or even death if not treated. The root cause is a deficiency in thiamine, or vitamin B1. Alcohol interferes with absorption of this crucial nutrient, and on top of that, many heavy drinkers suffer from poor nutrition in general. Studies show that 8 out of 10 people with alcoholism lack sufficient B1, leaving their brains vulnerable. Unlike the reversible dendrite damage, once neurons die due to this deficiency, the brain cannot fully repair itself. Even with treatment, Some impairments persist permanently. Another concerning effect is that alcohol, especially in very high amounts, suppresses the formation of new brain cells. For years, scientists believed adults were stuck with the neurons they had by the end of adolescence. But now we know that the brain continues to generate new nerve cells in certain regions, a process called neurogenesis. Alcohol interferes with this growth, slowing the birth of new neurons. In experiments with rats, once alcohol was withdrawn, the brain compensated by accelerating neurogenesis, producing fresh cells more rapidly to make up for the gap. Whether the same full rebound happens in humans isn't entirely clear, but it shows the brain has remarkable adaptive potential. However, if the cycle of heavy drinking continues for long stretches without recovery, it's possible that suppressed cell growth leaves long-lasting scars. Beyond these direct neurological effects, excessive drinking invites a host of other complications. Adolescents and children who abuse alcohol may experience neurological problems that appear almost immediately, disrupting development. Adults who binge regularly face heightened risks of conditions that stretch far outside the brain, such as liver disease and damage to the peripheral nervous system. So while neurons may not be dying off in droves, alcohol can still cause widespread harm. In simple terms, enjoying a glass of wine with dinner or a beer with friends on a regular but restrained basis can actually support long-term mental health. But turning alcohol into a habit of excess brings disruption and risk. Your body can compensate for some damage, especially if you allow time for recovery, but it cannot undo every effect of chronic abuse. Moderation is the crucial dividing line. There's also the amusing folklore around alcohol that has circulated through history. During Prohibition, wild rumors spread that people could spontaneously ignite if they drank too much, simply because alcohol is flammable. Of course, this is biologically impossible, but the story gained traction among fearful audiences. The myth that alcohol burns away brain cells gained steam in that same era, lingering long after laws changed. Myths often outlive facts, but scientific research eventually sweeps them aside. Even hangovers, while not caused by dying brain tissue, have their own biological explanation. Alcohol dehydrates the body by interfering with vasopressin, an antidiuretic hormone. With less of that hormone available, the kidneys produce far more urine than usual, draining the body of fluids and salts. The pounding headaches, thirst, and fatigue that follow a night of drinking are primarily the result of this dehydration, not the loss of brain matter. Modern neuroscience also shattered another outdated assumption: the belief that adult brains could never generate new nerve cells. Today we know neurogenesis occurs throughout life, especially in regions like the hippocampus, which plays a central role in memory and learning. Alcohol can slow this renewal, but it doesn't erase the process entirely. The myth that alcohol inevitably burns away neurons is as outdated as the belief in spontaneous combustion. The story of alcohol and the human brain is full of half-truths, exaggerated warnings, and fascinating discoveries. To understand it clearly, one must strip away the myths and focus on what actually happens inside the nervous system. For centuries, people have repeated that each drink destroys countless neurons, painting alcohol as a relentless cellular killer. Yet science shows a different reality. The damage isn't wholesale slaughter of neurons, but rather disruption of how they interact, how they repair themselves, and how the body supplies the nutrients they depend on. Consider the brain's immense complexity. With roughly 100 billion neurons working in harmony, supported by even more glial cells, the system is designed with redundancy. Signals flow through intricate dendritic networks, and when some branches are harmed by alcohol, the rest of the system can compensate. This explains why most heavy drinkers, despite years of abuse, don't collapse into immediate brain failure. Their minds may slow, coordination may falter, But actual neuron death from alcohol alone is not the driving factor. Instead, the trouble lies in how those neurons are able or unable to communicate. Stopping heavy drinking often allows much of this lost functionality to rebound. Dendritic spines regrow, communication pathways reconnect, and normal signaling resumes. This resilience is why someone who has been drinking heavily for years can still recover much of their clarity if they quit. But there are limits, and those limits become obvious in conditions like Wernicke-Korsakoff syndrome. When alcohol blocks absorption of thiamine, the deficiency starves neurons of what they need to survive. Here, the cells don't just struggle, they die. The result is memory loss, hallucinations, motor dysfunction, and a cascade of symptoms that medicine can sometimes treat but not fully reverse. The prevalence of thiamine deficiency among alcoholics highlights another problem: nutrition. It isn't just alcohol acting chemically on the body, but also lifestyle factors that go along with it. People who drink heavily often eat poorly, and their bodies are doubly robbed, once by alcohol interfering with absorption, and again by diets lacking essential vitamins. This combination magnifies harm, pushing the nervous system to the edge. Another layer of complexity is the impact alcohol has on neurogenesis, the creation of new neurons. Decades ago, the prevailing belief was that the adult brain was static, incapable of producing new nerve cells after a certain age. That assumption has now been overturned. We know that even adults generate new neurons, particularly in regions vital for memory and learning. Alcohol, especially in high doses, slows or even halts this process. In laboratory animals, once the alcohol stopped flowing, the brain kicked into a rebound phase, producing new neurons at a rapid pace to make up for lost time. This suggests a remarkable ability to recover, but it also underscores a critical fact. Without recovery periods, long-term suppression of neurogenesis may leave lasting consequences. Beyond the direct neurological issues, alcohol's impact radiates through other organs and systems. The liver, as the primary organ processing alcohol, suffers greatly. The nervous system outside the brain can also be damaged, creating tingling, weakness, or numbness in the limbs. These issues remind us that while the alcohol kills brain cells, mantra is misleading. Alcohol abuse still wreaks havoc throughout the body. The harm is broad and systemic, even if the brain's neurons aren't dropping dead with every sip. Still, moderation paints a different picture. Studies repeatedly show that small, regular amounts of alcohol, such as a glass of wine per day, can provide protective effects, particularly in older adults. The mechanisms aren't fully understood, but may involve improved circulation, reduced stress, or mild stimulation of certain neurotransmitter systems that keep the mind resilient. These benefits vanish when drinking tips from moderation into excess, but the fact remains: alcohol is not solely destructive. Like many substances, its impact depends entirely on dose, context, and consistency. Cultural myths about alcohol reveal how fear and misunderstanding shape public opinion. The idea of spontaneous combustion fueled by alcohol in the veins is laughable today, but it was once repeated as fact. The belief that alcohol tortures brain cells with every swallow endured for generations, bolstered during Prohibition when scare tactics were used to discourage drinking. Myths are memorable because they're simple and dramatic, while the truth is nuanced and harder to package into slogans. Yet careful studies dismantle these misconceptions, leaving us with a more complicated but more accurate story. Even the unpleasant experience of a hangover illustrates this complexity. The pounding head, the spinning stomach, the overwhelming thirst. None of these are signs of brain cells burning away. They are primarily the result of dehydration. Alcohol suppresses the hormone vasopressin, which normally signals the kidneys to conserve water. Without it, the body expels far more urine than usual, draining fluids and electrolytes. The brain feels the consequences not because neurons have died, but because the body's fluid balance has been thrown off kilter. Restore hydration and salts, and the symptoms gradually fade. What emerges from all of this is a clear principle. Alcohol's relationship with the brain is not one of immediate death, but of stress, interference, and recovery. In small doses, the brain may even adapt in ways that offer protection against age-related decline. In large doses, however, the cumulative effects on nutrition, communication between neurons, and neurogenesis stack up to create long-term impairment. The danger isn't in a single night of drinking, but in a lifestyle where excess is the rule rather than the exception. The modern understanding of neuroplasticity reinforces this point. The brain is not fixed. It remodels, regenerates, and adapts constantly. Alcohol disrupts that flexibility but doesn't obliterate it outright. The same adaptability that allows someone to recover after quitting heavy drinking also makes the brain more vulnerable when abuse continues without pause. Balance then becomes the crucial factor. It's also worth noting the social dimension. Alcohol has been part of rituals, celebrations, and daily life across cultures for millennia. Its role isn't only chemical, but symbolic, tied to human connection and tradition. That dual identity, as both a toxin and a tonic, makes alcohol unique. It can harm, but it can also serve as a bridge between people, easing conversation, marking milestones, and even, when used wisely, supporting health. So when someone asks whether alcohol kills brain cells, the truthful answer is more layered than a yes or no. Pure ethanol destroys cells on contact, but drinking doesn't flood your brain with enough to cause mass neuron death. What it does is interfere with how those neurons talk to each other, how they grow, and how they are nourished. The brain, astonishingly resilient, can recover from much of this, provided the drinking is curtailed before permanent damage sets in. Ultimately, the message is one of moderation and awareness. A little can be protective, too much can devastate. The line between the two is thinner than many imagine, and once crossed repeatedly, consequences multiply. Myths about exploding bodies or instant neuron death may be false, but the reality of chronic alcohol abuse is sobering enough on its own.